to you, my viewers and subscribers. Welcome back to the channel. Welcome back to another video. So I trust that everything is good and everybody is okay. So in today's video, I'm going to show you a swimming pool that I have designed for one of my subscribers sometime, I think, in the earlier part of last year, 2023. So this is the swimming pool here that I want to bring to your attention, viewers and subscribers. So initially, this swimming pool was not a part of the drawings, was not a part of the initial design. But what the owner recommended, that since he has a rear balcony, a balcony at the back, he's going to attach a swimming pool to it, so that the occupant of his building can leave and come out on the back balcony and enters down into the swimming pool. So if you observe carefully where you have this cut line here, there is the balcony in concrete here. So you have the steps here going down into the pool. So the dimension of the pool is 18 feet in length by 12 feet in width. Now, this pool is reinforced concrete, as you know already, and it is supported by beams and columns. So here is a call out for the reinforced concrete beam. The reinforced concrete beam is 14 inches in width by 18 inches in depth. The column, the base of the column here, is 14 inches by 14 inches. And the thickness of the wall for the pool is 1 foot 2 inches or 14 inches. I'm going to explain to you and show you the structural calculation, how I get my thickness of my wall to be 14 inches or 1 foot 2 inches. So that explains the plan view of the pool, right? So I'm going to move now to the section of the pool, the cross section of the pool. So let me zoom up here so I can show you the reinforcement. So this is the cross sectional view of the pool, right? So if you observe, so we have here, this is the balcony here, the slab of the balcony here. If you notice, it is attached to the wall of the pool. So on one end, the height of the wall is 4 feet, and on the opposite end, the height of the retaining wall of the pool is 5 feet. Now, the reason for that, we increase the depth of the pool towards the opposite end. So we have a slope here that moves down from a thickness of 1 foot 7 inches down to a thickness of 8 inches. So on one side of the pool, the thickness of the slab is 1 foot 7 inches. On the opposite side, the thickness of the pool is 8 inches. So the 1 foot 7 inches comes to this point here, and it slopes down 17% to this point here to 8 inches. So if time permit me, I will show you how I get the slope to be 7 inches. You know that to calculate the slope is the rise over run times 100%, times 100. So it is the height divided by the length times 100, and that's how you get the percentage slope. So if you observe, if you look at the reinforcement in the retaining wall here, so this vertical bar here coming up from it's going to lap here though, it's going to lap from the column up into the wall of the pool. So that rebar is 3/4 of an inch and spaced at 6 inches on center. So that's the front face. The inner face where the water is going to rest on the wall. On the outer face, the outer face reinforcement, it is a 1/2 inch spaced at 6 inches on centers. And these bars here, these little dots, these are your distribution bar. So someone might look at this and say, why so much reinforcement? 3/4 inch bars, number 19 bars, spaced at 6 inches on center. The reason for that is that I'm going to show you too, that the thickness of the wall, when I did the initial calculation to get a factor of safety of 2, the thickness of the wall works out to be 3 feet. Now, I didn't want to design a pool with such a thickness. That's too elaborate. So what I did was to cut down on the thickness of the wall and use reinforcement to compensate for the inadequate thickness. I'm going to show you the structural calculation for that. Now, as you can see here, you have our beam reinforcement, 1, 2, 3. And if you notice, the top bar in the beam goes up into the slab of the pool. And the top mat of the pool here, it is number 5 or 5/8, spaced at 6 inches on center. On our distribution bar or temperature and shrinkage bar is spaced at 1/2 inch on is 1/2 inch bar spaced at 8 inches on center. So that pretty much takes care of the cross section. And if you observe the amount of columns that I use to support the pool, it is 3 and 3, 6. It is 7 columns, right? 7 columns. And when you look at the cross section here, you can see 1, 2, 3. So I cut it so I can see 3 of the columns. So the section is cut right about here, right about this line here. I should have drawn the section line, section cut, so you can see, right? And if you notice, I have mentioned this to you already, it is a 14 by 14 inch column, right? So let's move to the column detail now. So this is the column detail here. As you can see, the width 1 foot 2 inches or 14 inches, and this is the base of the column here, right? Showing the reinforcement, and this is number 6 or 3/4 19 millimeter mild steel bar as vertical reinforcement in square portion of column, right? And here I have these at the end. I have these hook bar here, and these hook bar here, it is used for earthquake purposes, since the footing carries a double mat. In the event that we have any seismic action, any earthquake, the top mat and the bottom mat here, they move in unison and they don't break away from each other. So if you notice on one end, it shapes a particular way, and the opposite end, it shapes another way. So it's rotated. So these are your hook bar or earthquake bar. We use them here on bridges. So I just decided to put them on, since that is a typical footing detail for a bridge, right? Now let me move to the beam detail. So as I said to you before, the beam is 1 foot 2 inches thick, right, by 18 inches in depth. So that work out to be 18 inches by 14 inches, right? I've shown you that already on the plan view of the pool. So if you notice, in the tension zone of the concrete, I have 4 number 16 or 5/8 inches bar. I'm going to show you how I get that to be 4 5/8 bar in the tensile zone to carry the load. And here we have these bars here, this bar here, this bar here, this bar here, and this bar here, and that is for temperature and shrinkage. So it's temperature and shrinkage and flexural bar. Now the shear reinforcement, The shear reinforcement I use 3/8 bar at 6 inches on center, because when I did the shear calculation, the shear was pretty high, and I think I was getting something like 10 inches on center, but because the weight of the water on the column and the beams is going to be constant, I decided that I was going to decrease it from 8 inches or 10 inches down to 6 inches, just to be sure. So if you know the modes of failure of a beam fails in two modes. A beam can fail through flexure or through bending or through shear. So it is critically important that when you're designing a beam, you design your main reinforcement to carry the load, and you design your stirrups in terms of your spacing to withstand against your shear moments. So shear and bending, that's for your beam. All right, so that's pretty much takes care of a quick synopsis of this pool. I have talked to you about the plan view of the pool. I've briefly go over the section view, the column view, and the column in this is the plan view of the column here. I didn't mention this, but it's the same thing here, right? If you observe, it is 1, 2, 3, 3 and 3, 3 and 3, 6 and 2. So it's 8 number 6 bars, 8 3/4 inch bar. So that's a pretty heavy bar there, reinforcement there to withstand the pool. I kind of go a little bit over on the design here, just to ensure that the pool can withstand the members can withstand the weight of the water in the pool. All right, so that's for that. Okay, next I'm going to talk to you about how I determine the width of the width or the thickness of the retaining wall of the pool, and I'm going to show you how I get the reinforcement in the beam to be 4 5/8 bar. All right, good. So I'm going to go over the wall calculation, the retaining wall calculation for the pool. So I use a height of 5 feet, and remember I've said to you in earlier that the height of the wall on the opposite end is 5 feet, right? So this is a wall here. So since this wall is higher than this wall here is going to come under more stress because of the increase in height. So I just use this wall here of 5 feet high because it's going to come under more pressure. All right. So now when you're designing a retaining wall that retains soil or water, it carries a triangular pressure distribution. And the reason why it is a triangle pressure distribution is that pressure increases with depth and decreases in height. So if you're in water, the further down you go into that water, the further down you submerge that body down into the water, is the more pressure that body is going to come under. And as that body starts to come up out of the water, the pressure is going to decrease because there's going to be less water acting on the body. So the reason for the triangle, at the top here, the pressure is going to be 0. But as the body starts to descend, submerge down into the water, it's going to get wider and wider and wider because the pressure increases. All right. So the unit weight of water is 62.4 pounds per cubic feet, or 1,000 kilograms per meter cube. So the maximum pressure is going to be at the base of the triangle here, which is going to be gamma H, and gamma is the unit weight of water. So if you times the unit weight by water by the height of the wall, we are going to get a result of 312 pounds per square feet. So it is going to be 62.4 pounds per cubic feet times 5 feet, and that works out to be 312 pounds per square feet. Now, to calculate the force is going to be the area of this triangle. Alright, so we can use the force, which is going to be half gamma h squared. Alright, or we can say half times the base of the triangle, which is 312 pounds per feet square, times the height, which is 5 feet, and that works out to be 780 pounds per foot. So what this is saying is that every foot along this wall, there's going to be 780 pounds. So every unit foot along the length of the wall, that force that is going towards the wall is going to be equivalent to 780 pounds. Right? So it's 780 pounds per foot. Now, to withstand the weight of the water, we have to design the thickness of the wall. Because the only thing that we have to resist against the weight of the water resting on the wall is the weight of the wall itself. So we know the height of the wall, we do not know the thickness of the wall, but we can come up with the thickness of the wall through mathematical calculation. So we know that the unit weight of concrete, since we're going to use reinforced concrete, the unit weight of reinforced concrete is 150 pounds per cubic feet. So we're going to times that times the volume of the wall times the center of gravity to get the moments, right? So for the wall to be stable, the overturning moments must be equal to the restoring moments or the resisting moments. So the weight of the wall is going to be 150 pounds per cubic feet times 5 feet times 1 foot, because we are talking about 1 unit length. When we are designing a structural member, we do not design for the entire length, we only design for 1 unit length. Whether it be feet or meter, we design for 1 foot or 1 meter. So we're going to times that now by the thickness of the wall, which we don't know, times the center of gravity of the wall, right? Which is going to be T over 2, because we are taking moments right about the center of the wall here, which is going to be T over 2. Now, so that is for the restoring moment. Now, the overturning moments now is going to be force times the lever arm. Now, the resultant of this force that is acting on the wall, based on the fact that it is a triangular pressure distribution, is going to be the height divided by 3. So the center of gravity of a triangle is the height divided by 3, right? So the force is going to be that 780 pounds times the height of the wall, which is 5, divided by 3, right? 1/3 height. That's the resultant force of that is the resultant force acting on the wall, right? So it's going to be 780 times 5 over 3, right? And that works out to be 2,600. And we have on this side here, we have 1,500 pounds per foot times t squared. So we want to find t squared. So it's going to be 2,600 divided by 1,500, which is 1.73. And since we want to find t squared, we have to find the root of 1.73 feet, which gives us a thickness of 1.31. So we want to convert this 1.31 foot or feet, and we times that by 12 inches, so we're getting 15.72 inches, and we roll that up to 16 inches. Now, 16 inches, we have to establish a factor of safety. So we want to find out if this 16 inches is adequate for the thickness of the wall to resist the moments of the water resting on the wall in order for the wall to be stable. So I'm going to use a factor of safety of 2. So the factor of safety is going to be the restoring moments or the resisting moments divided by the overturning moments, which is going to be greater than 2. When we work that down into the equation now, the result where we divide the overturning moments, where we divide the restoring moments by the overturning moments, the result is 0.5, and that's not okay. So I have to do some iteration, trial and error, and I ended up get the wall to satisfy a factor of safety of 2 to be 3 feet thick. Now, in my estimation, I didn't want to use a 3 feet thick wall because I think that is going to be too much money in terms of, to build a 3 feet thick wall all the way around with rebars is going to cost the guy too much. So I decided that I was going to cut back on the thickness of the wall and go back to a wall thickness of 1 foot 2 inches, and that is why I have so much reinforcement in the wall to compensate for the inadequate thickness. So the real thickness to satisfy the factor of safety of 2 of this retaining wall should be really 3 feet. But because I want to cut down on that thickness, I use a thickness of 1 foot 2 inches and put heavy reinforcement in the wall itself to compensate for the shortfall in thickness. So that's how I get that thickness to be 1 foot 2 inches. So I'm going to quickly show you the beam calculation. So the beam calculation is a lot of calculation went into it. So I use this beam here to govern the design. So I'm not going to go through the design. All I'm going to talk to you about is the area of steel. So the area of steel works out to be 1.24 inch square. So if I'm going to use half-inch bar, it's going to work out to 6 half-inch bars. But I decided that I was going to use 5/8 bar, and because it's going to be 5/8 bar, it's going to work out to be 4 5/8 bar. And that's how I get the swimming pool cross section of the beam to be 4 5/8 bar in the tension zone. All right, so that is how I come up with the design for the wall here. And of course I did my checks. I calculate my minimum reinforcement to see if my minimum reinforcement meet the requirement of the bar. So the minimum reinforcement here for a beam that size is going to be 0.84 inch square. So I'm getting a area of steel of 1.24 inch square, which is adequate. So if you want, you can go through the calculation, right? I'm going to leave it in the description here. For those of you who want to learn or to see how I come up with the calculation, you can do that. So that is pretty much how I get my reinforcement for my beam. So that is it for this video. If you like the video, make sure to hit the like button. Subscribe. I want to reach at least 5,000 subscribers by the end of this year. And please do watch the ads as well. So enough respect. Big up on yourself. And me talk to you again. Alright? Respect, man.